Newton's first and second laws of motion, and calculating forces. Consider a book that has been placed on a table. The book cannot now move of its own free will. It can only move if, for example, it's pushed by someone. And this pushing force is an example of what we call an external force. This then neatly leads us into Newton's first law of motion. An object will remain in equilibrium unless it is acted upon by an external force. And we're going to discuss what that word equilibrium means. If an object is in equilibrium, the forces acting on it are balanced, and the overall resultant force, which is what we mean by the overall combination of the forces acting, has zero effect. Now, this means there are two possibilities. For an object in equilibrium, it must either be stationary or travelling with a constant speed, i.e. it has zero acceleration. Let's have a look at two examples. Firstly, an object is at rest on a surface. So let's draw a very simple force diagram for this. Here's our object, and let's add in some forces. We've got the weight acting vertically downwards. We have the normal reaction acting vertically upwards. And these two forces are balanced, so the normal reaction will be equal to the weight and the object is at equilibrium on the surface. If I decide to push on the object with some kind of pushing force, then assuming that the surface is rough, there will be a frictional force which works against my pushing force. Now, if I start pushing, I may not push hard enough to be able to overcome the frictional force, and the object may still remain in equilibrium. To break the equilibrium, my pushing force has got to be greater than my frictional force, and at that point the object will start moving, it will start accelerating, and equilibrium will be broken. In the second example, we have a car travelling at a constant speed. So here's our road. We'll model the car as a particle travelling on a rough road. The weight acts downwards and is balanced by the normal reaction upwards. We have a driving force in the engine of the car. Now, because the car is travelling at a constant speed, we know that this driving force must be equal to the resistance force or the frictional force working against the driving force, opposing the movement of the car. So, as the car is travelling at a constant speed, we know it's in equilibrium. So this tells us that horizontally, the driving force must be equal to the frictional force. If the driver of the car wants to accelerate the car, then the driving force will have to become greater than the frictional force in order to break the equilibrium. So the forces then are no longer balanced, and we would have what is called a resultant force in the forwards direction, which would take the car forwards. We'll be talking about resultant forces in a bit more detail. So let's talk about equilibrium and resultant force in a little bit more detail. We have two very similar examples. The first example, an object is placed on a rough surface. It is pulled with a force of 10 newtons and the size of the frictional force is also 10 newtons. Let's label the forces in our force diagram. We have the weight acting vertically downwards. We have the normal reaction force acting vertically upwards, there is a pulling force of 10 newtons forwards like this, and then the friction is 10 newtons in this direction here. So this is our pulling force and this is our friction. This object will remain in equilibrium. The forces are balanced. And there is 0 resultant force. We can see that the forces pulling the object forwards are equivalent to the forces resisting that motion in the opposite direction, so there is no overall resultant force in that horizontal direction which would allow the object to move forward. Let's look at a second example. This time an object is placed on a rough surface. It is pulled with a force of 40 newtons and the size of the frictional force is 10 newtons. Let's label the forces on the force diagram. Again, there's the weight of the particle. This is the normal reaction of the surface pushing up on the object. Our forwards pull force is 40 newtons and the size of the frictional force is 10 newtons. Now this time there is a resultant force of 30 newtons in this direction, going left to right. This means that the object is not in equilibrium, and we can see that forces are not balanced. As a result, there will be an acceleration, and we'll talk in a little bit more detail about how to calculate this acceleration. The last example leads us towards Newton's second law of motion. We can express this in a number of different ways. The one you're most likely to see is that resultant force is equal to mass multiplied by acceleration. So the resultant force acting is equal to the mass of an object multiplied by its acceleration. Symbolically, if we're talking about resultant force, you will often see sigma F, and you've seen that symbol sigma previously, which means the sum of, which is another word for resultant. We'll be dealing with the concept of force as a vector and acceleration as a vector as well, so quite often you may see people write out Newton's second law in its vector form as well. So we would say that the vector sum of the forces, i.e. the resultant force, is equal to mass multiplied by the acceleration vector. Let's look at some examples to illustrate this. We're going to draw some force diagrams, think about modelling, and then use Newton's second law of motion to perform some calculations. So, example 1. An object of mass 3 kilograms is placed on rough horizontal ground. It is pushed with a horizontal force of magnitude 40 newtons, and the size of the frictional force is 15 newtons. Calculate the object's acceleration. So, force diagram. Here is my rough horizontal ground. Here is my object of mass 3 kilograms. So it will have a weight acting downwards. We'll be talking about how to calculate weight a little bit later on. There will be a normal reaction force to balance that, acting vertically upwards. The object is pushed with a force of 40 newtons. So I'm going to put that force in this direction, going left to right. It could go in the opposite direction as well. I've just chosen to draw my diagram this way. Because the object is acted upon by a 40 newton force which is trying to push it from left to right, the frictional force has got to oppose this direction of motion, so the friction must be in this direction like this. Now, we need to calculate the resultant force. So we need to make sure we think about which direction things are happening in. So if we look at what's happening, we've got 40 newtons to the right, 15 newtons to the left. So overall, that is a resultant force of 25 newtons. So resultant force equals 25 newtons going left to right. we know that the resultant force is equal to the mass multiplied by the acceleration. So 25 is equal to 3 multiplied by acceleration. So the acceleration of this object is 25 over 3 meters per second squared. Example 2. A car travels a distance of 32 meters along a straight road while uniformly accelerating from rest to 16 meters per second. By modelling the car as a particle, find its acceleration. Given that the mass of the car is 600 kilograms and the engine is exerting a driving force of 3,200 newtons, calculate the magnitude of the resistance experienced by the car. So there are some key words here. Uniformly accelerating. That means the acceleration is constant. And that implies that we can use our constant acceleration or our Suvat equations. So let's write down the information that we know. We know the distance travelled is 32. The car starts from rest and accelerates up to 16 meters per second. We're trying to find out the acceleration and we do not know what the time is. So the Suvat equation that we are going to use is v squared equals u squared plus 2as. Let's fill in some information. And then we can calculate our acceleration. This is equal to 4 meters per second squared. We're now going to draw a force diagram for the situation. Here is our car being modelled as a particle. We have a weight acting downwards and a normal reaction acting upwards. So the engine is exerting a driving force of 3,200 newtons, and there must be a resistance experienced by the car, which we'll just call F over here for friction. So the car is clearly accelerating, which means that it's moving in this direction with an acceleration of 4 meters per second squared. So I'm going to take going to the right as a positive direction. Resultant force equals mass multiplied by acceleration. So the mass of the car is 600 kilograms and its acceleration is 4. So the right hand side is easy to fill in. Now the resultant force has got to be 3,200 take away F. And that is our resultant force. Remember, the resultant force is the sum of the forces acting, and forces are vector quantities. You have 3,200 in this direction, which is positive, and you have F, which is in this direction, which is effectively a negative because it's going in the opposite direction. If you add those together, you get a resultant force of 3,200 minus F. And this is then a really simple equation that we can rearrange to calculate our value of F, which equals 800 newtons. Example 3. A particle of mass 600 grams is acted upon by 3 forces. Find the acceleration of the particle and the magnitude and direction of this acceleration. So a number of things to notice here. First of all, we're given the mass in grams, but actually if we're using the force F equals ma, force measured in newtons, mass has got to be measured in kilograms, and acceleration has got to be measured in meters per second squared, so that we are working in standard units. So 1 newton is equal to 1 kilogram per meter second squared. So our mass, which is 600 grams, has got to be written as 0.6 kilograms before we can use it carefully. Now, the forces have been given as vectors. So when we're using f equals ma, really we're thinking about this in the concept of vectors. I'm going to write these as columns. 7, 13, that's force F1, plus 4, 4. This is, of course, how we add vectors together. You've learnt about the resultant of vectors, which simply means you're combining or adding vectors together. And the third vector, minus 2, minus 5, third force. This is equal to the mass of the object, 0.6, multiplied by its acceleration, which we will find as a vector. So if we add together the vectors on the left-hand side, our I component has a value of 9 and our j component has a value of 12. Divide both parts of this by 0.6 and we will have the acceleration vector. So our acceleration vector is 15, 20. Now, to find the magnitude and direction, we need to draw this vector or a sketch of this vector. So that's 15 across, 20 up, not to scale, so our acceleration vector looks like this. So the magnitude of the acceleration, remember the modulus of the vector, can be calculated using Pythagoras' theorem, which comes to a value of 25 meters per second squared. And the direction, well, there are lots of different ways in which we can do that. We can calculate this angle theta using trigonometry. And this gives us an angle of 53.130 or 53.1 degrees. So we can say the direction is 53 degrees above the horizontal, or we could provide a bearing, which would be this angle